Welcome back to Math 104. Jordan received a 70 in Section 3 with mean score 60 and standard deviation 7.1. Jordan received a score better than approximately what percentage of the students in Section 3? Measured in standard deviations, there is some number z here, such that Jordan scored z standard deviations above the mean. That z-score is computed as exam score minus mean, all divided by standard deviation, and that turns out to be 1.41 standard deviations above the mean. We look up z equals 1.41 in the table. We find 0.4207 as the entry corresponding to 1.41, so 42.0% of the class scored above the mean but below Jordan's score, and another 50% of the class scored below the mean and certainly below Jordan's score. As a result, Jordan received a score better than approximately 50% plus 42.0% of the class, and that is 92.07% of the students in the class. We can put it all together now and make apples-to-apples comparisons. Of the three friends, which one had the highest relative standing in his or her section, and which had the lowest? Alex received an 82 in Section 1, with mean 75 and standard deviation 4.2. We found that there the z-score was 1.67. Alex scored 1.67 standard deviations above the mean. Similarly, Chris scored 1.73 standard deviations above the mean, and Jordan, we just found, scored 1.41 standard deviations above the mean. In relation to the rest of his or her own section, Chris had the highest relative standing, and Jordan had the lowest relative standing. Still better than 92% of the class, but not quite as spectacular a performance as Chris or Alex relative to their sections. Notice that the normal distribution is so clustered about the mean that by the time you're roughly 1.5 standard deviations above it, you have a score higher than well over 90% of the rest of the data. This brings us to another important application of the normal distribution, which is grading on the curve. Now this term, grading on the curve, has come to mean something like everyone just gets 15 bonus points added to their raw score. Traditionally, however, grading on the curve means something else. Here's an example. Professor What's-His-Name uses the following system for assigning letter grades, but don't worry, this is not the system used in our course. The mean final exam grade was 74, with a standard deviation of 8.3. The idea behind grading on the curve in the traditional sense is that the letter grade cutoffs are set in advance and measured in standard deviations. In this particular example, students scoring at least 0.9 standard deviations above the mean received an A. Students scoring between 0.25 and 0.29 standard deviations above the mean received a B. Students scoring between 0.75 and 1.5 standard deviations below the mean received a D. And students scoring at least 1.5 standard deviations below the mean received an F. All others received a C. This is one way of defining what the grade distribution will be in a course. Thus, the cutoff for an A is at z equals 0.9. Everything above that is an A. The cutoff for a B is at 0.25, so any score which is between 0.25 standard deviations above the mean and 0.9 standard deviations above the mean receives a B. Then we are told that anything 0.75 standard deviations below the mean, anything between that and 1.5 standard deviations below the mean receives a D. Anything beyond 1.5 standard deviations below the mean receives an F, and anything that remains receives a C. Once again, this is not the system used in our course. We can ask what range of scores, that is, what range of exam scores, corresponds to each letter grade. We can also ask what percentage of the class received each letter grade. The cutoff for an A is at 0.9 standard deviations above the mean. This means that the cutoff exam score for an A was 74, that's the mean, plus 0.9 standard deviations above the mean. 74 has 0.9 copies of 8.3 added to it to find the exam score cutoff for an A. To say it another way, we take the mean 74 and we add 0.9 measuring sticks. We start at the mean, we go 0.9 measuring sticks up, and in points that brings us to 81.47 points. To find what percentage of the class received an A, we look up 0.9 in the table, that's 0.90, we look that up in the table. and we discover the number 0.3159. But we have to remember, 0.3159 is the probability of landing in this region here between the mean and our cutoff for an A. So 31.59% of the class scored above the mean but fell short of an A. That means that we need to compute 0.5 minus 0.3159 to find that 0.1841 of the class, that is 18.41% of the class, received an A. What about a B? The B range is in between 0.25 standard deviations above the mean and 0.9 standard deviations above the mean. By the same reasoning as before, the cutoff exam score for a B was 74 plus 0.25 copies of our measuring stick. That brings us up to 76.075. We're allowing cutoff scores here that are not whole numbers because we have no idea how Professor What's-His-Name grades. Maybe he goes down to 7 decimal points of accuracy. So there is a point to having these exam score cutoffs not be whole numbers. It follows that the B range was between 76.075 and 81.47. Recall that 81.47 was the cutoff for an A. So that's the upper end of the B range. What about the percentage of students receiving a B? Now we've already found that 0.1841 is the probability of landing in the A range. When we look up 0.25 in the table, we come up with 0.0987. Now let's think where the 0.0987 lives. That describes the region between 0 and 0.25. So 9.87% of the class scored better than the mean, but they missed the cutoff for a B. What does that say about the percentage who received a B? We have to compute 0.5, that's for the entire right half of the picture, minus this 0.1841, and also minus that 0.0987. It's this region in here that we're trying to find the probability of. If we take the entire right half of the picture and throw out the two regions within it that we don't need, we'll end up with the probability of the region that we do need. That turns out to be 0.2172. Thus, 21.72% received a B. The remaining information is that students scoring between 0.75 standard deviations below the mean and 1.5 standard deviations below the mean are in the D range. Students scoring at least 1.5 standard deviations below the mean received an F. All others received a C. That means the C range spans territory to the left of the mean and to the right of the mean. Before going on to the next video, find the range of scores corresponding to a C and what percentage of the class received a C.